Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to describe what is called RMS voltage and RMS current. So in my previous video on the series I talked a little bit about AC voltage, and an AC voltage is a voltage that varies periodically with time. The most common is a sine wave type of voltage. So we're going to talk about just a sine wave type voltage today that looks like some sort of Vmax sine omega t. This is the symbol for AC voltage, right? And in most of my videos, if you've been watching these, this is the symbol for DC voltage. This circle squiggly thing represents AC voltage. So we're going to imagine trying to, run something like a light bulb off of an AC voltage source. That's what this picture is supposed to be. The circuit diagram for this, I would replace the light bulb with a resistor, right? And then again, here's my AC voltage source. And what we're going to do here is we're going to chat about what's called the RMS values. Let me get rid of those. All right. So for starters, in our circuit here, remember, this is an equipotential, right, conducting material, and then on the other side, so this Vmax sine omega t is the potential color-wise described by red to black, and you'll notice that potential is good across this resistor, red to black. So this voltage is good here. Now, if I were to calculate an average voltage across the resistor over one complete cycle, you would end up getting 0, because this sine wave is symmetrical. Half the time the voltage is positive, half the time the voltage is negative. Now, the light bulb would be on the overwhelming majority of the time. The light bulb doesn't care if the current is in one direction or the other. So the way the average voltage and average current is calculated is through the concept of power or energy. So what's called the RMS voltage, VRMS, right, is defined as the DC voltage with the same power. If I were to put a picture of that on here, I'm going to do this in green, the RMS voltage is less than the peak. And that's because the voltage, it's 170 volts, or it's at its peak here, and this keeps going here, and so forth. But the overwhelming majority of the time, the voltage is something less than 170. So we're going to go ahead now and try to calculate, all right, what does that RMS voltage look like? Find some sort of expression for it. We're going to do that by using energy concepts. Starting with power. So power, remember, is rate that energy is transferred. So in the language of derivatives, we could write that dE dt. And what we're going to do is we're going to calculate the energy that has been, we'll say, dissipated by the resistor for one cycle for both the RMS voltage and our sine wave. So this can be solved for energy easily. dE is equal to power times dt. Now, power in circuits can be expressed several different ways. Power is equal to current times voltage. It's also equal to current squared times resistance. It's also equal to voltage squared over resistance. I'm going to go ahead and use this one here. Now, this picture here reminds me of something that I probably should have introduced in the last video. Variables. As a general rule of thumb, DC currents and DC voltages are represented with capital letters, like I've kind of written out right over here. So if you see something like this would generally mean a DC current, whereas AC currents and AC voltages, generally people use lowercase letters to represent. That's why I've got a little I here, and I had intended a little v here. But anyway, we're going to use voltage squared over resistance to calculate the energy. So we're going to have dE is equal to the power. Now I'm going to go ahead and do this for my AC voltage source. Voltage squared over resistance is going to be Vmax sine omega t squared over R, this thing's resistance, times dt. The total energy then dissipated for one cycle would be the integral of this expression from 0 to 1 period. All right, so now we're going to take a look at this integral a little bit more, and I need more room. So we're just going to get rid of this stuff right here. All right. Okay. So, as usual, anything that's constant can come out in front of the integral. Now, you notice we have a V max squared over r. That can all come out in front. And then we're left with integral 0 to 1 period, 0 to t, of sine squared omega t. Let me write this over here. Sine squared omega t. Now, standard integration techniques here. That sine wave can be rewritten in terms of a cosine wave, and I believe it's 1 minus cosine of 2 omega t over 2. I'm just going to take a minute here to kind of jog my memory here. Sine squared x, I think that's 1 minus cosine of 2x over 2. Yeah. Okay, I think we're good. Memorization of all these different types of functions in that is not my, or theorems is not my strong suit. All right, so when we go ahead and keep going with this integration here, all right, so we got this V max squared over r, right? Now, integral of 1/2 dt is going to give us, evaluate at these limits, that's going to give us t over 2, or period over 2, minus, all right, now this integral here, antiderivative of cosine of 2 omega t is sine of 2 omega t over 2, and there's already a 2, so that's going to become a 4. This one has yet to be evaluated. All right, so now I'm going to take this guy here real carefully. If I put a t here, right, if you take a look at the sine function, 2 omega t, 1 period puts us here. Second period, this is going to keep going, is going to put us here. Third period, fourth period. This thing, when I put any multiple of this period in, you're going to get a 0 out of this. Sine of 0 is 0. And when you put 0, you also get a 0. So this thing right here is just gone. All right, so what we got is that the energy dissipated for one cycle, we've got this expression here. V max squared over r times t over 2. Now the t I have a numerical value for. It's a 60th of a second, but I'm just going to leave it like this because we're not going to need it. All right, now what I'm going to do is do the same thing for the RMS voltage. So dE dt can be expressed in terms of a DC voltage as V RMS squared over R times, well, I'll just leave it like that, multiplying both sides by dt. And noting that this is all constant, we just end up with V RMS squared over R times the period. By time we do the same thing, integrating this 0 to 1 period. All right, and that's not a dE anymore, that's now a, oops. Now this guy, oh, I should actually write this out, all right. If we integrated this expression 0 to 1 period there, that's what we would get. All right, so now what we're going to do is we're going to compare this to this. And you'll notice that if I write out this guy equals this guy, the r's will be gone, the periods will be gone, and what we will be left with is we're going to be left with V max squared over 2 is equal to V RMS squared. All right, so the RMS voltage is equal to the peak voltage over root 2. And that's how you go from this right here, this relationship here is how you go from a maximum voltage to an RMS voltage. And again, the US power grid has a peak of about 170 volts. So Vmax is 170. And when you take 170 and divide by square root of 2, right, you get 120 out of that. So that's why all the devices that you buy, when you look at the back of them, they'll say they're designed to run off 120 volts. Now sometimes you'll see at 110. You know, this is not a perfectly exact science. The design of the peak is supposed to be 170, but you get line losses and losses in your house and things like this. So usually by the time you get to your wall outlet, which remember is this guy, sometimes this voltage has fallen off a little bit. Generally speaking, your power is considered good if this is anything higher than 110 volts, but I usually just say 120 is kind of the standard. RMS currents can be calculated the same way. What's called your RMS current, I'll put I RMS is equal to your peak current, I'll put I max over root 2. All right, so this over root 2 part, this is how you go back and forth between peak current and RMS current, or peak voltage and RMS voltage. The 1 over root 2 is specific to a sine wave. If you have other types of voltage waveforms, and there are others, right, you would have to go through this process. You integrate over one cycle, setting the energy on your AC function to the energy over your DC function. But you know, other types of functions you may encounter are what are called like square wave voltages. Those might look something like this. Or you might see some sort of sawtooth looking voltage. It might look something like this, and so forth, in which case you'll get different values than the 1 over root 2. Anyway, just meant to be an introductory video about RMS voltage and RMS currents. I hope that this has described these reasonably well for you. Have a great day.